All right. Hey folks, Adam Ward here. I want to just work through one example of using the Arrhenius equation in a few different ways to understand the role of temperature on reaction rates and practice with this a little bit. So for this setup, I've ginned up the following problem. Consider that we have a first order reaction describing the degradation of a compound. We'll call it methyl ethyl bad stuff for now. We know from laboratory tests that there are first order rate coefficients of 0.5 per hour and 0.9 per hour at two different temperatures. And so the question is, how long will it take to remove 50% of the starting concentration? And not written here, let's say that's at the 25 degrees C, so that's the typical sort of ambient temperature, let's say. Part B, what is the theta for the reaction? And then part C, what would that half-life be if we changed the temperature to 30 degrees C by heating this up? So working through this, for our first order reactor, we know that the concentration at any given time can be described by this equation. And we can replace that left-hand side, because we know our target concentration is half of C naught. We'll replace C of T with 0.5 times C naught. And you can see I've written in the appropriate rate coefficient up there in the exponent. Those concentrations cancel out. We didn't have them, but that's not a problem. And we can solve this for a time of about 1.4 hours. So for this rate coefficient of 0.9 per hour, it should take us about 1.4 hours to get to half of that initial concentration, no matter what the initial is. For part B, we're asked to actually find that theta that describes the equation. And so we remember that the ratio of those K values can be described as equivalent to that theta raised to the difference in the temperatures between the two, T2 minus T1. And so plugging in information from the two temperatures that we were given, we've got one equation, our only unknown is theta, and we can go ahead and solve that out for a theta value of about 1.12. So now we know our theta value, and part C then asked us, what is the half-life for this equation, or this chemical reaction we're interested in, at a temperature of 30 degrees Celsius? So we'll remember that there's two important equations here. One, what is that half-life? And again, that T half is 0.693 over K. Then the second thing we'll need is that Arrhenius equation to correct our rate coefficients and pick the right K for 30 degrees C. So starting on that second equation, we know the rate coefficient at 20 degrees C. We know the theta value, and we know the temperatures that should go in the exponent. And I'll note here, I'm picking the temperature and rate coefficient from 20 degrees. You could also use the pair from 25 degrees Celsius and it would work just fine. So we get a new K value of about 1.55 per hour. And we can take that K value and plug it back into that first equation. And what we learn is that if we move up to this temperature of 30 degrees C, it drops it down to about 0.45 per hour. So for this made-up reaction that we've described here, that was about 1.4 hours. So by raising the temperature by 5 degrees Celsius, from 25 degrees, which we considered in part A, to 30 degrees, which we've considered in part C, right, that 5 degree centigrade difference actually means it takes us about 1/3 of the time to get that reaction to proceed. And so this is just a nice illustration of the role that temperature control plays. If we want something to proceed more efficiently, we can add heat to accelerate that problem. Hopefully this example gives you some practice working with the Arrhenius equation and understanding these relationships between temperature, rate coefficients, and this theta that allows us to pivot between them. Thanks for your time and attention, everybody.